Good afternoon. Thank you, Pablo, for the introduction, and thank to everyone in attendance for this talk. Today, I'm going to present some of the research that I did under Pablo's supervision in the past 5.5 years. This is going to be on the analysis and methods of multi-phase flow and interfacial phenomena, some with application in medical devices. So let's start with a quick overview of what I'm presenting. I will begin my talk with presenting my work on flowing soap film that we published last year. Then I will present my water entry project by focusing on the splash curtain that was published in 2020. Next, my data assimilation method for analyzing cavitation bubble will be discussed. This work was also published last year. Next, I will present the results of one of the most challenging data I dealt with on the interactions of a gas bubble and cavitation bubble. This work has been submitted to PRL recently. In the end, I will present my analysis of two interfacial phenomena in autoinjector medical devices. These two work have been submitted to Lilly, or it's going to be submitted to Lilly soon for the clearance. So with no further ado, let's start with the first topic. In the first section, I will discuss our findings on a viable experimental setup for replicating nearly 2D flow called flowing soap film. Flowing soap film system typically consists of a nearly planar film with a thickness of 10 microns and a free stream velocity of 1 meter per second. Local variation in flow speed, such as caused by a bluff body obstructing the flow, for example, produce small variations in the local film thickness that correlates with the pressure variations and can be used to identify flow structures such as coherent vortices. The value of the flowing soap film as an experimental platform depends on its ability to approximate the 2D Navier-Stokes equation. So our objective is to verify the correlation between interference fringe patterns and underlying flow structures by simultaneously obtaining PIV data and interferograms and comparing the vortex center arrangements in soap film with those reported in the literature for case of low Reynolds number. We also introduced a quantitative soap film thickness measurement method using background-oriented Schlieren or BUS to provide a spatially resolved thickness field. You can see different sections and components of a flowing soap film on the left, and on the right we are showing our unique visualization system that can be employed to conduct simultaneous PIV and interferometry, as well as phase match interferograms and BUS. To achieve our goals, we designed a test matrix with 4 different sets of experiments and visualize the flow behind the stationary cylinder with different techniques. Here I'm showing a qualitative comparison between the vortex scores obtained from simultaneous PIV and interferometry that shows an agreement between the two. The left panel is the interferogram image, and the middle panel is the obtained vertical structure from PIV data. And on the last panel on the right, I'm putting the center of vertical structure and the center of soap film patterns on the interferogram image. And next, we can review the correlation of the relative film thickness obtained from BUS and the interferograms qualitatively. Vortex scores in the cylinder wake appeared as low thickness zones. The red markers on the interferogram are the local, it's hard to see, but they are the local minimum thickness of the film. And to quantify the error, we find the discrepancy between vortex scores obtained from different techniques in these plots that does not show any significant difference. Now that we show that these techniques provide interchangeable methods of identifying vortex centers in the wake of a stationary cylinder, we can compare the vortex structure with those reported in the literature. We start with vortices arrangement of vortices in the wake of the cylinder at different Reynolds number agree with those reported for the 3D flow. The left panel shows the average streamwise spacing of vortices as a function of Reynolds, and the right panel shows the transverse spacing as a function of both stream-wise location, and for different Reynolds number. Formation length of the vortices in the flowing salt film also correlates well with those reported in the literature for the case of low Reynolds number. And lastly, I'm calculating the circulation, and the circulation of vortices in the flowing salt film has the same magnitude as those reported by other researchers. So I can summarize the contribution of this work. I mean, the main contributions of this work can be summarized as, for example, validating the use of a flowing salt film system as a 2D laboratory model of flow past the cylinder at low Reynolds number. We also introduced a quantitative method for determining the relative film thickness and verified the correlation between interference, fringe patterns, and underlying flow structures by simultaneously obtaining PIV data and interferograms. We also demonstrate the correlation of vortex strength and vortex center arrangements in the salt film with those reported in the literature, only for the low Reynolds number case. The second interfacial or multi-phase flow phenomena that I investigated was the water entry of hydrophobic spheres. A crown-like splash curtain is formed every time an object impacts the water surface. The water entry phenomena is present in a wide range of applications, from the entrance of torpedoes into the water or to divers jumping into pools at the Olympics. And it's always accompanied by a splash. This surface curtain may splash outwards or dome over and close, referred to as surface still. The dynamics governing the splash curtain evolution and closure have been unexplored. And to date, we don't know why sometimes the surface curtain still and other times it does not. In contrast to our current understanding, which labels the projectile impact velocity and the corresponding Weber number as the primary cause in the occurrence of surface still, our observations show that this phenomenon is not fully defined with the impact velocity. When kept a Weber constant and varied density and size of the sphere, we could not see a threshold Weber beyond which the surface still occurs. Here in these plots, I'm showing that, for example, for a Weber of 800, the splash curtain of spheres with a smaller size and higher density was closed, but the cavity of larger and lighter spheres remained open to atmosphere. So to find out the governing parameter of surface closure, we look at the forces acting on the splash curtain. These forces include the drag force, the centrifugal force, gravitational force, surface tension, and pressure difference force. We also wrote the equation of motion for the beta trim of the curtain. We could formulate all the forces, but the pressure difference force. So we took a data assimilation approach and decided to look at the changes in the cavity volume, which is formed behind the spheres, and write Bernoulli's equation to find the pressure difference based on the airflow velocity rushing into the cavity. So after updating the pressure difference force, we solved the equation of motion to find the rim trajectory. And as the videos show, the model predicts the rim trajectory well. Another observation that we had also shows that the surface still occurs for the cavities with higher rate of volume change that corresponds to higher pressure difference. We know from the model that the airflow velocity controls the pressure difference. So we hypothesize that there is a critical U air over U naught, which is U naught is our impact velocity. We hypothesize that there is a critical U air over U naught beyond which the surface still occurs. So we revisited the model, and through a scaling analysis, we showed that the surface still time, or the time that it takes for the curtain to reach its maximum height, is scaled with U air over U naught. And we could find a critical U air over U naught beyond which the surface closure occurs. In this plot, the open markers show cases with no sill. The solid markers represent the cases with surface still, and the blue vertical area is the predicted transition from no sill regime to surface still regime from the model. So therefore, we revealed that the splash shape strongly depends on the pressure difference between the entrant air and the atmosphere. In the following 3 chapters, we are going to investigate cavitation dynamics as an interfacial phenomenon that is present in nature and engineering, and govern processes from corrosion to propeller blades to drug getting through the endothelial cells. Cavitation is a phenomenon in which vapor cavities are formed in the liquid when the local pressure drops below the vapor pressure of the liquid. Cavitation bubble can be generated by a laser or acoustic waves too. The nucleation and its position are accurately controlled for the laser-induced cavitation, and the induced bubble is approximately spherical. These allow for the close study of the bubble dynamics with this method. When a pulsed laser beam is focused in the water medium, water molecules are broken down by the laser energy, and hot ionized plasma is generated. After the laser is switched off, deionization occurs in nanoseconds that releases energy by instantly heating the water, which induces an explosive bubble with extremely high pressure and temperature inside it. The temperature and pressure decreases with the bubble's expansion, and the evaporation rate in this phase is larger than the condensation rate. When the bubble radius reaches its maximum, it is filled mainly with vapor and only a small amount of air. The temperature inside the bubble is approximately the ambient temperature, but the pressure inside the bubble is smaller than the surrounding pressure. So the bubble begins shrinking, and the condensation rate becomes larger than the evaporation rate. In this process, the bubble surface is heated, and a thin, super high temperature region is formed around the bubble surface. When the bubble collapses to its minimum volume, the pressure inside the bubble can reach hundreds of atmosphere pressure, and the temperature can reach 10,000 Kelvin degrees, which can induce a chemical reaction inside the bubble too. Since the collapse of the cavitation bubble is so violent that it generates an intense shock wave and induces high shear stress on the surrounding liquid, we need a high temporal resolution method to characterize this moment. The low temporal resolution of experimental data suggests that a model-based analysis of this problem would be preferable. However, high-fidelity models are not always available, and even for these models, the sensitivity of the model outputs to the initial input parameters makes this method less reliable, since some initial inputs are not experimentally measurable. Therefore, we propose a robust characterization tool based on a novel data assimilation technique to overcome these 2 challenges in the existing methods. This technique fuses the time-resolved cavitation bubble diameter measurements with the governing model to yield enhanced spatiotemporal prediction of the cavitation bubble dynamics. By assimilating experimental measurements into the cavitation models, we can overcome the challenges in the parameter estimation of the model inputs, account for the lack of knowledge about this phenomena, compensate for the underlying assumption in these models, decrease the sensitivity of the model output to the initialization, and make accurate predictions. This technique places an observer variable in the governing equation and uses a proportional integral derivative, which is known as PID control law, on the difference between the predicted and measured cavitation bubble diameter. In other words, when the predicted bubble diameter by the model and experimentally measured value have a discrepancy, an error term is calculated and is fed to the PID controller. The controller then generates a source term in the original model equation and iterates until error goes below a certain value. For example, for the Rayleigh-Placet equation, the second order differential equation for the radius is this equation here. And the control signal will be placed on the right-hand side of this equation to fuse the measurements into the Rayleigh-Placet equation. The obtained equation and the additional equation from the cavitation model are solved for the cavitation bubble radius. And for the sake of validation, we selected to apply PID controller on 3 cavitation models with different fidelity levels, namely Rayleigh-Placet, Yasui, and Jarn. However, the method is general and can be applied similarly to any other cavitation bubble dynamics model. For the validation, we generated a laser-induced cavitation bubble in a small chamber at different laser powers to obtain a variety of bubble diameters and recorded pressure with 2 hydrophones and captured images with a high-speed camera. In these plots on the right, which shows the hydrophone reading, the cavitation collapse is distinguishable by its high amplitude in the pressure signal. Therefore, the pressure amplitude is picked as a comparison parameter between the hydrophone measurements and predicted pressure by the cavitation models. Let's see how the size prediction responds to the data assimilation. In these plots, we have the original model's prediction in blue and start increasing the number of assimilated data points into these models and plot them in red. By increasing the number of assimilated data points, the assimilated model predicts the bubble size more accurately. These plots indicate that we need to assimilate more experimental measurements for the daily placid, which is our low fidelity level model, to get the same error as Young, which is our high fidelity model. Next, we compare the estimated collapse-induced pressure amplitude, which is computed by original cavitation models and assimilated versions. The plot shows the error between hydrophone measurements and predictions by original and assimilated versions for the first 3 collapses. Each panel in this figure corresponds to one model, and the most significant deviation between models' predictions and measurements is observed at the first collapse, where Rayleigh-Placet predicts the pressure amplitude with around 70% error on average. Nevertheless, assimilation of measurements with Rayleigh-Placet result in more than 80% improvement in the estimation of far-field pressure. And even though Young has the best performance in predicting the far-field pressure, integrating measurements into this model can improve the estimation by at least 50%. With this, I guess I can conclude this chapter by highlighting the contributions of this work. The data assimilation modeling most accurately estimates the bubble diameter and far-field pressure. Although the simulated model is not a substitute for high-fidelity models, this technique overcomes some limitation. For example, the inherent model assumptions such as bubble stricity and chemical reactions within the bubble that are difficult to be modeled, and makes the model's output more robust with respect to the physical parameters' initial values. We use this method in the following 2 chapters to quantify the pressure field induced by cavitation and to measure the strength of cavitation that occurs in autoinjector medical devices. In this chapter, the video's in play. I'm gonna use a cavitation bubble as an acoustic source for exciting gas bubble and studying the bubble-bubble interaction, which is a fundamental problem. And also looking at the interactions of the air bubble with the acoustic source from an energy transfer perspective, which can have application in containing oil spills, reducing shock wave propagation, and analyzing other environmental and industrial problems. So let's get started with setting up the problem. And to study the interactions of a single air bubble with an acoustic field induced by a cavitation bubble, we inject air bubbles of 5 different sizes at the bottom of an acrylic chamber, which is filled with distilled water. On the left, you see a schematic of our experimental setup. And to control the acoustic field intensity, the cavitation bubbles are generated on top of the air bubble at the center of the container using a laser at 3 different laser powers. We record the dynamics of both cavitation and air bubbles using a high-speed camera. The far-field pressure is also recorded using 2 hydrophones. And we also vary the relative distance between the 2 bubbles by using a photodiode detector to delay the cavitation inception. The table on the right shows the range of each parameter and some dimensionless parameters as well. Okay, okay. These are not gonna play. I'm sorry about that, but I'm gonna explain it just good enough. Once the cavitation bubble is generated, the air bubble starts oscillating in the volume oscillation regime. The volume oscillation means the radial expansion and contraction of the bubble without varying its shape. As soon as the incident acoustic wave is sufficiently intense, the oscillation surface of the air bubble becomes unstable due to the forcing of large amplitude volume oscillation, which leads to the onset of shape oscillations. These videos were supposed to show the effect of air bubble size and relative distance between the bubbles on the air bubble oscillation regimes. We observed 4 different oscillation regimes: volume oscillation, single mode shape oscillation, multi-mode shape oscillation, and breakup. The video was supposed to indicate that it's more likely to oscillate in shape when the air bubbles are closer to the acoustic source. Also, the larger bubble has less intense oscillation at the same distance from the acoustic source. So we could hypothesize that the absorbed energy by the gas bubble controls the oscillation regime. But before we test our hypothesis, we need to develop a robust way of oscillation regime determination and a method to find the absorbed energy by the bubble. So we proposed a frequency-based approach to define different oscillation regime. In this approach, the air bubble volume variation over time signal, which is obtained from the highest speed imaging, is analyzed with the continuous wavelet transform to find the dominant frequency of size variation over time, which is this plot on the top right. I don't know if you see my cursor, but the top right plot. Next, the time history of the dominant wave number of the air bubble boundary is obtained. And lastly, the air bubble oscillation modes are achieved by plotting the time history of the boundary wave number against the dominant frequency of size variation over time, which is the last plot, the bottom right plot. And with this, we could define that the air bubble undergoes a volume oscillation regime if we observe 1 mode. If we exactly observe 2 modes on the map, the final oscillation regime that air bubble undergoes is single mode shape oscillation. And if the map shows multiple modes of oscillation, the bubble final oscillation regime is multi-mode shape oscillation. Moreover, in more intense acoustic fields, and when the air bubble is closer to the acoustic source, the bubble may break into single or multiple tiny bubbles while undergoing multi-mode shape oscillation. Hence, we define a new regime as breakup for such cases. But this regime is automatically detected during the image processing step when we observe more than 1 bubble in any of the frames. Now that we can determine the oscillation regime, we define the discrepancy between I don't know what's wrong with this slides, but anyway, we define the discrepancy between the pressure signal energy in the presence and absence of the air bubble as the absorbed energy. We can measure the pressure signal energy in the presence of the air bubble using hydrophone data. And to find the energy of the signal in the absence of the air bubble, we use the data assimilation approach and predict the far-field pressure, which is induced by the cavitation bubble. Now we can estimate the absorbed energy by comparing the hydrophone signal energy and the predicted signal energy by the assimilation model. In these plots, the solid black line represents the hydrophone readings in the presence of the air bubble, and the blue dashed line shows the predicted pressure energy in the absence of the air bubble. Now we can, okay, this is definitely not good. Okay, just give me a second to see what's going on here. Okay, sorry about that. We conducted a parameter study by varying the air bubble size, cavitation energy delay, cavitation generation delay, and laser power, plus elucidating the influence of cavitation energy, relative distance, and bond number on the air bubble final oscillation regime. This plot here illustrates the air bubble oscillation regimes map based on the induced cavitation energy and a modified bond number that includes the distance between the air bubbles and cavitation bubble size. At high modified bond number, the air bubble is stiffer, which means the either which means bubble needs more energy for the formation and transition to another oscillation regime. It's also possible that the air bubble is further from the acoustic source, hence the excitation energy at the air bubble location is not high enough to cause a transition to shape oscillation. On the contrary, at low modified bond number, the air bubble is smaller or closer to the cavitation nucleation site, thus the induced energy yields in the breakup of the air bubble. In these two extremes, cavitation energy has the least impact on the oscillation regime since the bubble is closer to the acoustic source or further from the acoustic source. However, in the moderate modified bond number, the air bubble oscillation regime transitions from volume oscillation to single mode shape oscillation to multi-mode shape oscillation, and to finally break up as cavitation energy increases. For the shape oscillation, our observations show that the transition from volume oscillation to shape oscillation is a function of cavitation energy, the relative distance, and the air bubble size. Hence, we hypothesize that the acoustic energy absorbed by the air bubble controls the ripples onset on the air bubble surface. To investigate this, we first conduct a scaling analysis on the Rayleigh-Clase equation and non-dimensionalize the absorbed energy. We know that the absorbed energy by the air bubble increases the bubble's internal energy. And the internal energy is the sum of the work which is done on the surrounding liquid by the changes in the air bubble's volume and the changes in the surface energy due to changes in the surface area. And lastly, the changes in the kinematic energy of the bubbles, which can be formulated as those equations on the left. When we substitute the formulations, we find a linear relationship between the dimensionless absorbed energy and a modified Weber number defined based on the acoustic intensity in terms of induced pressure that agrees with the experiments. This plot shows that the modified Weber can determine the critical thresholds for oscillation regime transitions. So our analysis showed that, oh my God, what's wrong? Why this video is playing fine here? I don't know. Our analysis showed that different oscillation regimes could be defined robustly based on the Weber number of the air bubble boundary. It was shown that the transition between different regimes was controlled by the air bubble absorbed energy, and the absorbed energy was a linear function of Weber number. In the next two chapters, we focus on the interfacial phenomena occurring in the autoinjector medical devices. That could be harmful to the therapeutic protein that these devices are to deliver to patients. The first phenomena that we study is cavitation, but before that, let's see what an autoinjector is. Autoinjectors are devices that are used for self-administration of therapeutic proteins. Most of them are one-use, disposable, spring-loaded syringes. And the main components of these devices, a spring-driven autoinjector, are syringe, driving rod, plunger, air gap, syringe, needle, and drug. When the device is activated, the rod accelerates by the compressed spring and hits the plunger. And consequently, the air gap is compressed and pushes the drug through the needle into the skin. Cavitation in autoinjector happens due to high acceleration during the insertion phase and the subsequent relative displacement between the drug and bottom of the syringe. The relative displacement causes the pressure drop at the bottom of the container, and if the acceleration is high enough, cavitation is formed. It can increase the number of particulates, cause a fracture in the syringe barrel, and impose high shear stress on the drug that can yield aggregation. When talking about cavitation, we are talking about a phenomenon that occurs in fraction of a millisecond. And when it comes to collapse, we are dealing with an event happening in less than a microsecond. So directly measuring the induced shear and pressure inside the autoinjector is quite challenging. If we want to put a pressure transducer and a strain gauge inside the syringe directly and measure the generated pressure wave and induced shear stress, we need to remove the needle, place the measurement tools, fix them, and put the needle back. So conducting this kind of invasive measurement can change the flow regime entirely inside the autoinjector, which is not desired. In addition, the location of cavitation formation is not predictable, and only a small portion of the drug is exposed to that high shear. Therefore, we are not sure where we should place those measurement tools to find the actual values. Also, if we place them close enough to the right nucleation site, the temporal resolution of the equipment we use is another issue. So it's better to look for a reliable high temporal resolution, non-invasive measurement that we would be confident that whatever we find is the same as the drug is experiencing. That's why we employ the data assimilation approach to take advantage of high temporal resolution of the modeling and reliability of experimental measurements to obtain reliable estimation for the cavitation stress. Once we find the severity of the cavitation in terms of the induced extension rate, we compare it with the protein activation limit. We investigate the effects of the spring force, air gap size, field volume, and viscosity on the severity of cavitation that occurs in the autoinjectors in terms of extension rate. We conducted our test in two different platforms, in situ and ex situ. In the in situ setup, we test the original autoinjector device, while in the ex situ one, we tear apart the autoinjector and reuse the components in our fixture for more optical access while capturing the images. Once we capture the images of cavitation, we find the equivalent diameter and fit them into the assimilation model to find the maximum extension rate induced by the cavitation. Our taste matrix includes three cases. In case A, we study the effect of a spring force. Case B has been designed to investigate the effect of the air gap, and results from case C reveal the impact of filling volume. Before I jump to the results section, I'm showing a sample case of cavitation in one of our tested autoinjectors to show the strength of our model to study the cavitation bubble dynamics. Okay, let's review some results and investigate the severity of cavitation as a function of a spring force. In case A, we tested syringes with two different volumes, 1 ml and 2 ml, and provided each syringe's results in one plot. These plots show that the maximum extension rate induced by the cavitation in autoinjector, which is actuated with different spring forces, and with what we have here, we can say a larger spring force makes a stronger cavitation. A larger spring force corresponds to a larger syringe acceleration upon actuation of autoinjectors. So when we consolidated the data from these two plots and plotted the max extension rate as a function of maximum syringe acceleration, as you see, we observe a linear relationship between the two. Therefore, a larger spring force results in higher acceleration, severe cavitation collapse, and a higher induced extension rate. Now we'll see how the air gap size affects the severity of the cavitation. Here, by air gap size, we refer to the distance between the plunger position and the surface of the drug column. And again, we have the 2 ml syringe and 1 ml syringe, and this time we are changing the air gap size from 1 millimeter to 4 millimeters at a constant spring force. The average extension rate in each configuration indicates that the most severe cavitation occurs in a syringe with a smaller air gap size. Now let's look at the effects of the drug column height in this syringe. Okay, for this part of the study, we have a 0.5 ml syringe, which we fill with two different target levels, 0.2 ml filling and 0.4 ml filling. It indicates that the severity of cavitation in the smaller filling volume or lower column height compares to the larger column height are 1 order of magnitude smaller. And again, as a larger spring force generates a stronger cavitation. Another parameter that we study is the effects of the existing air bubbles inside the syringe. The existence of an air bubble inside the syringe increases the risk of occurrence of cavitation upon actuation of the autoinjectors. These micro-sized air bubbles can be formed during transportation due to the mixing and or during the filling process. Either way, they act as a nucleation site for the cavitation and increase the probability of observing the cavitation bubble. Thus, another parameter that we studied was the size of these pre-existing air bubbles inside the syringe. For this investigation, we used the existing data from all 3 cases to generate this plot. And this plot illustrates the correlation between the size of pre-existing air bubbles and their induced extension rate upon collapse. The results indicate that as the pre-existing air bubbles becomes larger, they generate a larger extension rate upon collapse. Our observation showed that the most severe cavitation occurred at the bottom and corners of the syringes, where the lowest pressure occurred in our tests. To investigate this observation further, we provide a heat map showing the most probable spots for cavitation with the corresponding intensity. To create this plot, this heat map for each syringe, we use the existing data from case A and case B and put them all on top of each other. These 2 maps show that the cavitation intensity heat maps for the 1 ml and 2 ml syringe fills and indicate that the cavitation intensity at the bottom of the syringe is higher than that of the bulk fluid. Besides, cavitation mainly occurs near the syringe wall due to the abundance of nuclei, and the corresponding intensity decreases as it gets closer to the air-fluid interface. So to conduct this section, we evaluated the strength of cavitation in autoinjectors to make sure that the drug and container remained unharmed, and find out that the larger spring force generated a stronger cavitation. The most severe cavitation occurred in a syringe with a smaller air gap size. The severity of cavitation in the smaller filling volume compared to the larger column height was 1 order of magnitude smaller, and the probability of cavitation occurrence in a smaller fluid column height was significantly smaller. And lastly, less severe cavitation occurred in a more viscous fluid. The other interfacial phenomena that we observe in autoinjector medical devices is liquid slosh. By sloshing, I mean the intense motion of the air-liquid interface during acceleration and deceleration of the syringe upon activation of autoinjector. As you may remember, during the insertion phase of autoinjector operation, the syringe undergoes an abrupt acceleration deceleration that can cause occurrence of cavitation and a sloshing phenomenon. The sloshing can induce hydrodynamic shear and increase the interfacial area in the therapeutic protein, which can be harmful. So it's crucial to characterize this phenomenon. We experimentally investigate the induced interfacial motion and hydrodynamic shear due to sloshing in a simplified autoinjector platform, which is submerged in water, and explore the effect of AI design parameters such as air gap size, spring force, and solution type on the intensity of sloshing. Since we are interested in exploring hydrodynamic shear and air entrainment, we conduct simultaneous shadow graph visualization and PIV measurement and capture the air-liquid interactions. So we designed a set of experiments to study this phenomena in the autoinjectors. In these experiments, the syringe was submerged in a small water tank, and we brought in the laser beam from the sidewall of the water tank and created laser sheet in front of the camera. With this, we could capture the particle images to find the velocity field. Moreover, we used the same camera and employed an LED for shadow graphs. We tested silicone oil and water at the same viscosity and used 2 syringes for 2 springs for actuation, one 12 Newton spring force and one 17 Newton spring force. For 17 Newton spring force, we varied the air gap height from 2 millimeters to 6 millimeters with an increment of 2. And for 70 Newton spring force, we only tested one air gap and repeated the test 5 times per condition. The shadow graphs are used for first finding the instantaneous size distribution of the bubbles, and second, creating a mask for processing the particle images with the PIV processing toolbox. We employed a bunch of filters in our unique image processing algorithm. I'm not going to go through the filters. I just need to mention that the bubble detection step includes 2 phases. First, we detect single isolated bubbles with no overlapping. And in the next step, we employ Hood transport to detect the overlapping bubbles. This video shows the outcome of the image processing step. As you can see, as soon as the bubbles are separated from the initial larger bubble, the air gap, we can detect, size, and track them. And after applying the obtained mask on the particle images, we process them and obtain the instantaneous velocity field with our in-house PIV processing toolbox. And from there, we could compute the strain rate. Now let's review some results, starting with the effects of air gap height on the interfacial area and volume fraction of the liquid experienced a strain rate above a certain threshold. By increasing the air gap height, the interfacial area and the maximum volume fraction of liquid experienced the highest strain rate increase. Also, between water and silicone oil, the slosh-induced interfacial area and a strain rate was more intense in syringes filled with water. And interfacial area and volume fraction of the slush solution with a high strain rate was more significant for the larger spring force. To find the physics behind this behavior, we use the Fruit number to scale the interfacial area. The Fruit number is the relative importance of inertia force to external field force. Here we use the relative interface velocity as the characteristic velocity, syringe acceleration, and syringe diameter as the characteristic acceleration and length. The results show that the interfacial area and volume fraction of solution with highest strain rate decrease with Fruit number. And considering the fact that we use the interface velocity for computing Fruit number, in order to make this analysis more practical for medical device developers, we tried to find a correlation between interface velocity and AI design parameters. So we came up with a dimensionless number that is the multiplication of Weber and Struhal numbers. Therefore, using the AI design parameters, we can compute the value of Weber times Struhal and obtain the interface velocity. Then we go back to the left plots to after calculating the Fruit number, we can find the normalized interfacial area and volume fraction of solution with highest strain rate. So the main findings of this work can be summarized as follows. The larger air bubbles tend less to break into smaller bubbles, but it stretches upon activation of autoinjector. A strain rate sharply increased during deceleration, and maximum strain rate occurred at the end of deceleration phase. Silicone oil and water had the same order of magnitude strain rate. And lastly, interface area of the air environment decreased with Fruit number. Now let's summarize some of the contribution of the research that I presented. We developed a method to measure cavitation intensity in medical devices in a non-invasive way, and methods to quantify the liquid slosh in medical devices, as well as a method to measure the absorbed energy by an acoustically excited bubble. Also, we introduced interchangeable methods to identify vortex centers in the flowing salt films. And from a scientific perspective, we introduced a data assimilation approach for modeling cavitation bubble dynamics, employed BUS to measure the soap film thickness, explained why a splash curtain does not always seal, and we also discovered the relationship determining how the absorbed energy generates ripples on the bubble surface, their growth, and the ultimate bubble breakup. The project that I reviewed today can be followed and built upon in so many directions in the future. For example, the analysis that I had on the splash curtain can be used to help divers have a splashless dive. Single gas bubble cavitation bubble interactions study can be generalized to find the energy absorbance by gas bubble curtains, which is used to contain all the spills, reduce shock rate propagation, etc. And now that we can quantify the intensity of cavitation and liquid sloshing autoinjectors, a series of controlled experiments should be conducted to replicate similar conditions to understand whether the proteins aggregates under these conditions. Before I wrap up, I would like to review the publications I've had so far under Pablo's supervision. I've had 6 first offer, 7 first offer journal articles, and 6 second or third offer published works. These are also other manuscripts to be drafted soon that I've listed here. I also had 2 submissions to APS Gallery of Motion, Fluid Motion, 1 video entry and 1 poster, and a couple of conference presentation and proceedings. And at the end, I would like to thank Pablo for all his support and advice during this long road. And thanks to my colleagues from Ethel Lab, especially Dr. Bhattacharya, for his friendship and value and mentorship. A special thanks to my committee members, Dr. Ardakani, Dr. Dabiri, Dr. Solorio, whom I truly honored to have as my committee. I should also thank the collaborators who are not here today, but they were such a great help, from Eli Lilly, Dr. Shi, Dr. Collins, and Dr. Veyu. Professor Kalati from ETH, Professor Stremler from Virginia Tech, Professor Sonny John from Cornell, and of course, Professor Gomez from Purdue. And last but not least, my friends, dear parents, beautiful sister, and this little princess, who was born a year into my PhD and is the hardest part of being away from the family. With that, I'd like to wrap up and pass it to Pablo to open the floor for questions you may have. Thank you.
Great job. Thanks, Javad.